Alright, so what I'm going to do in this video is we're going to use an Excel spreadsheet to find the minimum speed required for the person to clear the pit. That means that their path will take them to a peak right in the center, and then they should come back to land just far enough on the other side, so that they make it across. The distance across the pit was 30 meters. And that's going to be an important dimension that we want to use to judge whether the person makes it across or not. Alright, so let me pull up Excel. Alright, so we want to vary the initial velocity, and we can put in numbers of our choice, such as 0, 1, 2, 3, and so on. If you drag this down, it'll continue the pattern. We want to go at least up to 25, because we showed last time that 25 made it overshoot by a lot. So we're looking for a speed in the middle where it's just enough. I want to set up the horizontal, vertical components of that velocity though. Okay. Alright. Now I'm just going to write in the formula above the column. Okay, so we want VIX equals VI times cosine of an angle A. My angle for the problem was 30 degrees. Alright, maybe I'll move that down, put that there. Alright, so when you type it in, you want to type in equals D7 times cosine of $8.7, and then do times 3.14159 over 180. That converts the angle from degrees to radians. So that's what I want to type into my box. So equals D7 times cosine $8.7 times 3.1459 over 180. Alright, now I should be able to just drag that down. Alright, that looks pretty good right there. I'll do the same thing for the vertical component of the Y. Okay, so let's do D7 times sine of $8.7 times 3.14159 over 180. The $8.7 makes it lock onto that cell. That's the reason the dollars was there. Okay, sine. Alright, drag that down. Yeah, that looks pretty good. So this last row is actually the row that we had used in the problem to show that it went too far, right? So now I want to make a new column for the time of flight. I'll just put that. Alright, so we had worked that out in the past. And maybe we'll just do that calculation one more time just to remind us of how it went. All right, so solving this hinges on the y displacement being 0. Because it starts off at y equals 0 and comes back to y equals 0. So that means that the delta y for the flight will be 0. And so we want to use the formula for acceleration in the vertical direction, setting this equal to 0, plugging in our acceleration, and then for VIY, you could leave it as VIY, or you could put VI sine theta. I'll just leave it as VIY because that'll be easy to call up from the spreadsheet. All right, then you just try to solve it for t. So factor out the t, of course. Then this t can just divide into the 0, so that goes away. So you get t equals 0, or t equals VIY over 4.905. I suppose it would be 2 VIY over AY. But AY is negative technically, so you should have a negative there. Or you could put this, and that would be fine. Because the A alone, with no Y on it, is assumed to be a magnitude. It's assumed to be positive. But when you do put the Y on it, it's assumed that it could hold a sign inside it, and it would hold a negative value. Sometimes that really confuses people. But yeah, either one of those formulas would be fine. So that's what we want to plug into the spreadsheet and just make a column for it, right? All right, we want t is going to equal VIY over, you could just do 4.905, which is fine. If you wanted to be fancy about it, you could make a column for the acceleration due to gravity. And just put in like 9.81 there. Then you could call that up as part of your formula. So we could do 2 times VIY over A, where A is the acceleration. All right, so we're going to want 2 times our VIY column, which will be F7, it looks like, for the first one. And then we'll want to divide by $7, which is, of course, this right here. All right, let's try to enter that with equals. All right. Yeah, that looks good because we did find that the flight of our person would have been 2.55 seconds, as I recall from last time. All right, so that's great. Yeah, before we had said that it took 1.38 seconds to get across the gap, but that is only based on the horizontal component of the 25 meter per second launch. So that's something that would change if the velocity of the launch changes. So we can't always go off that. Instead, what would be a better approach would be to, to see how far horizontally the cart goes before coming back. In other words, we would want to use the range of the projectile, like as if it were launched on level ground. That would be the range, is how far it goes horizontally from where it was launched. And that would really be the ideal way right now to judge what the best speed for getting across is. So we can do that. We just have to make a new column for how far our projectile will go. All right, so we already know how long it's going to take to get to the other point where it was launched from. So what we should do now is use the formula delta x equals vt, using the time that we found and the x component of the velocity. All right, so we said that this was going to be the time for coming back down, so just plug that right in. So we'll have Vix times 2VIY over the acceleration. If you remember, the Vx doesn't change. It stays the same all the time, so it doesn't matter whether you use Vx or Vix. So I'm going to make a new column for this formula in my spreadsheet. Then we'll know how far each of the hypothetical launches will go. Okay, so horizontal distance to returning is what you want. All right, so delta x equals Vix times 2 times VIY over A. That's one way to write it, but we could also just keep it a little simpler if we were to just simply write times t, where t is the time of flight, because we have a column for that, so might as well just call that up. That makes it easy. All right, so we'll do Vix, which is E7, times our time, which is G7. That's all we need. All right, so equals E7 times G7. All right, this is great because you can see here that the range was 55 meters, and that is what we found in the previous calculations. Yeah, right here, we said 2.55 seconds to return to the same height of the launch, and then we calculated 55.3 meters of a horizontal distance covered. And we said that was too much because the pit is only 30 meters across. What we want to do is look in our spreadsheet. All right, so somewhere between these two rows would be the best, ideal one to use. So I can insert a bunch of rows here. I can try 18.1. And let me look at it here. So 18.2, 18.3, 18.4. We're getting closer. 18.5. Okay, right there. So it's between 18.4 and 18.5. That's our ideal. Okay? That's doing it with the spreadsheet.